The diffusion here is defined as the mass transport by atomic motion. Mechanisms of diffusion include these gases and liquids, random. This is random motion is called Brownian motion. For solids, and this is vacancy diffusion or this interstitial diffusion. First, we talk about interstitial this diffusion. This is interdiffusion, so impurity diffusion. In an alloy, atoms tend to migrate from regions of high concentration to regions of low concentration. This is concentration composition. This depends on the composition here. So this is initial. Look at here. This is a figure. So this initially I have this is this color and also this dark color. So these different colors, the two different colors stand for two different atoms. So that means at the very beginning, so this is this is colorful atoms. We have 100%. The concentration is 100%. That means on this left side, we only have. So this is we call this is atom A, and on the right side we have only atom B, right? We call it MB. Here is the concentration profile. So this is at the very beginning, and after some time, and we can see that some dark atoms they migrate from the right side to the left side, and also on the contrary, the colorful atoms and they migrate from left side to the right side. You can see in the middle part of this region, we have both the dark atoms and also colorful atoms here. This is the percentage. The concentration profile is denoted using these two curves here. We can see this percentage of colorful atoms starts decreasing from here and goes here until it reaches 0. The same thing for this is the dark atoms. They just decrease from here to here until it reaches 0. So you can see in the middle region, and we have both the dark atoms and also the colorful atoms. And this is because of the diffusion over time. Any questions regarding this slide? No questions? So here is a diffusion example. And we have this copper, and this is copper, and so this is a nickel. So this is diffusion of copper atoms from the left side, where it has higher concentration of copper. Well, at the very beginning, it is 100%. It goes from left to the right, and also for nickel atoms, they go migrate from the right side to the left side, because on the right side, it has 100% as concentration. So after some time, we can see clearly that in the middle region, we have both the copper atoms and also nickel atoms. And here is the concentration profile, and we also have very similar one, just as the one shown in the previous slide, copper and nickel. Questions regarding this slide? No question. Then we talk about the self-diffusion. So this self-diffusion in an elemental solid, and atoms also migrate. So label some atoms. If you label some atoms, and label some atoms A, B, C, and D. Okay, and after some time, and you can see C moves from to here, A moves here, and B and D, they are both of them, and they just move to different locations. That means even though we do not have other atoms, even the atoms within this region and the atoms themselves also migrate, some kind of randomly migrate. Diffusion mechanisms. So vacancy diffusion, vacancy diffusion. So this is vacancy diffusion. Atoms exchange with vacancy. This here. Okay. Suppose we have vacancy at the very beginning. We have vacancy. So here, this is color. This is copper for copper. It moves from this original location here, to this is the vacancy. So then this one becomes vacancy and applies to substitutional impurity items. Be very, very careful. Substitutional impurity items. What are the substitutional impurity items? And last time I told you, and to have the substitutional impurities, the several conditions must be met. First of all, the size of these two atoms, and they must be almost identical, or the difference of radii between their radii is very, very small. And second one, they have very, very similar electronegativities, also valency, and so all these is conditions need to be met in order to have substitutional impurities. Be very, very careful about this. If you are not familiar about these conditions, that means you might start forgetting these fundamentals. I would suggest that you go back to the previous lecture notes and review lecture notes and refresh your memory. I think it is a very, very good learning strategy. The rate, vacancy diffusion rate depends on the number of vacancies, and that means concentration of the vacancies. We can call this one. And activation energy to exchange. Activation energy to exchange, here it mainly talks about the operating temperature here. So you can see after some time, so this is the colorful atom moves from the original location to this vacancy, and then the vacancy move here. So you can just see the vacancy is regard this vacancy as another atom, but another different atom with almost identical radius, and this is electronegativity. So this is increasing elapsed time. So after some time, this one is changing the location with this vacancy, and then so this configuration is resulted. So you can see here the vacancy comes here. Any questions so far? No question? No question? And then as the time goes, and so this one can exchange location with this vacancy. So here is a diffusion simulation, the simulation of interdiffusion across the interface. So this is the interface. Here is a bunch of item A, item A, a bunch of item B. We call this slide, and I'm sorry, so this one is copied from the Professor Anderson's book, and so this slide contains animation that requires the QuickTime and Cinepec the compressor. Click on the message or image below to activate the animation. And I'm sorry, so this animation does not work in my slide. If you are interested, you can come back to Professor Anderson's textbook to get this one. Before get this one, you need to get the electronic resources for this textbook. The rate of substitutional diffusion depends on vacancy concentration and also frequency of jumping. So this is understandable, right? Okay, and then we talk about the second diffusion mechanisms. So this is called interstitial diffusion. Interstitial diffusion, and we have smaller atoms that can diffuse from one location to another between atoms. So these are bigger items, and we have small items, which is a yellow. Is colored yellow. Position of the interstitial atom before diffusion, and then position of the interstitial atom, which is a smaller one, after diffusion. You can see this guy, the original location is here, but sometimes this guy moves here, move to another position. More rapid than vacancy diffusion because they are smaller and thus more mobile. And furthermore, these are more empty. There are more empty interstitial positions than vacancies, right? Because this guy's size is much smaller than the size of other existing atoms. And then we talk about how can we use this diffusion to achieve some engineering goals. And so this is the first application is case hardening. And I need to, before I talk about this one in detail, I need to emphasize that this one is very, very important concept, and I want you guys to memorize it. So if I ask you a question about this case hardening, you can use your own language to tell me how it works and what the benefits we can get from it. All right? So this is very, very interesting this application. Case hardening, as the name suggests, this is a case. We have a case here, and we harden this material by some means. And what this approach is, and we talk about this one here. A high temperature heat treatment during which carbon from the surrounding atmosphere diffused into the surface. So diffuse carbon atoms into the host iron atoms at the surface. Right? So example of interstitial diffusion is a case hardening gear. So this is case hardened gear. And the case means that we have a chamber. And we have a chamber, and we put these specimens to be hardened in the chamber, and then we put some atoms that contain carbon, because carbon atoms are very, very small than the iron atoms. So we can achieve interstitial diffusion if we put iron atoms and these carbon atoms together. These carbon atoms can be provided in the form of gas, for example, methane, CH4, or this is the liquid. It can be a liquid, or can be solid also. But solid, if we put a solid, the carbon material that contains the carbon, the diffusion process will be very, very slow. So usually we use either the carbon containing gases or carbon containing liquid. And for this is carbon containing gases are more commonly used in this case hardening. And so then you elevate the temperature. After some time, some small carbon atoms will diffuse on the surface of these specimens to be hardened in the case. And so in the case, did that make sense? Okay, two important points. First, you have a chamber. This is a sealed chamber, and you put a specimen to be hardened in the chamber, and then you provide some carbon-containing gases or carbon-containing liquids. Theoretically, you can provide carbon-containing solids in this chamber. But as I said, carbon-containing gases are most commonly used as a material to case harden these material, these specimens in the case hardening. So this is a chamber, carbon hardening materials, your specimen, and then you elevate the temperature of the chamber, and then you hold this is everything at this temperature for a certain amount of time, and then you will get case hardened specimen. So what benefits and we can get from this carbon hardening? I want you guys to write it down, okay? Because this is so important that I want you to know that and what benefits we can get by case hardening these specimens. First one, so this is we will improve this wear resistance of the surface. Wear resistance, and we will improve the wear resistance because we make the specimen harder. First, enhance the hardness of the specimen by diffusing the carbon atoms on the surface of the specimen. This is the first one. Second one, it is not. Second one here, and it introduces residual compressive stress. Okay, residual compressive stress is very, very important, and this is the beneficial consequence of case hardening. Why? Because residual compressive stresses can improve the fatigue life of the gear. Here, specimen, this specimen, special specimen is a gear. Why? Because compressive residual stresses can prevent crack initiation and crack propagation. I think, I hope what I said makes big sense to you. And I want you to know what benefits we can have from case hardening. First, we enhance the hardness of the material, surface hardness of this is the specimen in case hardening. And so we can have better wear resistance. Second, and we will have better fatigue life of this specimen because we induce compressive residual stress. Keep in mind, you must have, in order to get the benefits, you must induce this compressive residual stress instead of tensile residual stress. Because tensile residual stress is bad. Because tensile residual stress facilitates crack initiation and crack propagation. As a result, tensile residual stress is detrimental for the fatigue life of the components. Questions so far? I want you guys to review the materials, review the lecture notes after we finish the class before you go to bed in this evening, and to make sure that you understand how the case hardening is carried out and what benefits we can get from case hardening and why. So this is very, very important. So second example about the engineering application of diffusion. So this one is doping silicon with phosphorus for N-type semiconductors. So what is the N-type semiconductors? If you have taken the fundamentals of electronics, you might already know this concept. And in addition to the material science, manufacturing processes, computer-aided engineering courses, and I also teach the mechatronics and and also for these seniors. So in this mechatronics, I taught N-type semiconductors and also the P-type semiconductors. And silicon is the semiconductor. Okay, silicon is a semiconductor, and phosphorus is another material that can be doped in the silicon and to get the semiconductor. Please note that silicon itself is useless. it must be doped by either using phosphorus to get N-type semiconductors or by using borax to get P-type semiconductors. So I will talk about these concepts N-type and P-type when I teach mechatronics. I think most of you guys, your major is mechanical engineering, and so in your fourth year here, and you will take mechatronics, and then I will teach you N-type and P-type. So first of all, this is doping. Doping means that we just use a minute amount of some other elements, in this is the host elements to enhance substantially the performance of the host material. For this case, is phosphorus is the doping element, silicon is host element, and as I said, silicon itself is useless. So first, deposit on the phosphorus rich layers on the surface. So this is silicon. So we deposited P here is the phosphorus layers on the surface, and then we heat it. Okay, then we heat it, and then we result, and we have doped semiconductor regions. So this one, this one, this one. Why? Because when we heat, so this configuration, and so this is the we will have diffusion between silicon atoms, and this is phosphorus atoms. So here is this is 0.5 micrometer. I'm sorry, millimeter. So this is the magnified image of a computer chip. So these light regions is Si atoms. The light regions here is aluminum atoms here. So this is I just want to tell you guys and how we use this and how we use this diffusion to accomplish some engineering goals. Any questions so far? No question. And then we move on to next one. Then diffusion. How can we quantify diffusion? So diffusion. How do we quantify the amount or rate of diffusion? And we use a J, and J is a flux. And J is flux, moles or mass diffusing divided by surface area multiplied by the time. So this is a mole, centimeter square, and also here is the time, or this kilogram, meter square on time. So measured empirically. So this make how can we measure it empirically? Make a thin film and this membrane of known surface area. Right? How can we do this experimentally? Then we impose concentration gradient, and measure how fast atoms or molecules diffuse through the membrane. And so J equals M A T time, and D M dt. So I is this is A here, and this is the time can mass diffused. We talk about the word gradient, and what is a gradient? Can somebody tell me? Can someone tell me what how we define gradient? And gradient means this. Gradient always means how something some quantity changes with respect to the locations. All right, so different locations and how some quantity changes. So this is called gradient. Then we talk about steady state diffusion. The rate of diffusion independent of time. So this is a steady state diffusion. A flux proportional to concentration gradient. The flux proportional to concentration gradient. Right? Concentration gradient, as I said, gradient means that you can see how the concentration changes with respect to the position x. The position is one dimensional. and we just assume this one-dimensional. In the vertical direct dimension, we do not consider the diffusion. So we are C1 and we have C2, and we use the fixed first law of diffusion, and J equals negative d dc dx. D is a diffusion coefficient. It is related to what kind of material you are talking about, and the temperature, maybe other factors that can determine this is a D. So we have a minus sign here. Can somebody tell me why we have a minus sign in front of D? Okay, we have minus sign because always this diffusion occurs in the direction from the high concentration to the low concentration. So this is opposite to the gradient. Okay, gradient, because gradient, as I said, gradient is an exchange of something with respect to the location, position. So because this is the opposite, and we should have a minus sign here. Do you have sense? Okay, then we move on to the next slide. So we can see if this linear, okay, if this linear, and dc dx or del c delta x can be approximated using this one. We can c2 minus c1 x2 minus x1. If linear, and we can have dc can be dc dx can be determined using this equation. And here is one example on how to calculate this is how to quantify this diffusion. And this example is chemical protective clothing and CPC. And in this problem, methylene chloride is a common ingredient of paint removers. And besides being irritated, it also may be absorbed through skin. Skin is very bad. We don't want to absorb these kind of chemicals. When using this paint remover, protective gloves should be worn. Right? So this is a problem statement. And if butyl rubber glue gloves, it's a butyl rubber gloves, and the thickness is given, are used. And what is the diffusive flux J of this methylene chloride through the glove? We want to calculate. So this is the diffusive flux. The data, we have diffusion coefficient in butyl rubber, D is given, and C1 is a concentration, and surface concentration, and C2 we are here surface concentration. And then how to solve this problem? We just use this equation, and we have J here, D is given, C2, C1, X2, X1, and they are given. X1 is the thickness, or glove thickness. So here, see, this is a paint remover chemical. And so here is our skin. And so because on our hand, on the this worker's hand, he or she wears the glove. And so here is the thickness. And you just plug in, and you can see J, you just plug in these parameters in the equation. This J equals this one, this value. And it is highly recommended that after the class, you just plug in these parameters to get hands-on experience of calculating this J by yourself. I think this one makes big sense for learning. And then we talk about non-steady state diffusion. The concentration of diffusing specifies in its species is a function of both time and position, C, and C is a function of X, position, T. So in this case, we use a fixed second law. We cannot use a fixed first law. Fixed first law for steady state diffusion. So fix the second law, and dc dt equals d, and so you can see second derivative of c and with respect to x. So non-steady state diffusion. Copper diffuses into a bar of aluminum. This is one example. Surface concentration. Surface concentration of these are copper atoms is given here. This is a pre-existing concentration C0 of copper atoms. And so boundary conditions. At the very beginning, we have C0 and C concentration C0 for x and to the infinity. This is for x from 0 to infinity. If at t is greater than 0 and C equals Cs, the surface concentration for x0 at the very beginning, and constant surface concentration, and C equals C0 when x reaches the infinity. So this is the boundary conditions. BC means here boundary conditions here. So here is CS, CXT, C0. This is position. We have it goes this temperature for the T1, T2, T3. So we know that different time at the same location, we have different the copper concentration because of diffusion. The solution, and we use this equation. So okay, don't worry that okay, don't panic, and I will not ask you guys to memorize this equation, and I will if I want to test your understanding of this problem, and I will just give you the equation and give you problem statements, so you know how to use this equation to solve our engineering problems instead of memorizing this equation. So CXT is concentration at the point x at time t, and ERFZ is error, the function, right? So this is defined using this equation. Integration, this is E, this is power negative y squared, and the values are given in table 5.1. So here, so this is a table of error, the function values, and Z, ERFZ, Z, ERFZ, Z, ERFZ.